Now let's look at the proof of theorem 6.6, which is the transformation of the convolution of two functions. Before we prove it, let me first identify what we need to show. On the left-hand side, we have the transformation of this integral of the two functions. That's the convolution integral. On the right-hand side, we have the product of two transformations, which are two integrals. Integral of e to the negative st little f and t equals 0 to infinity of e to the negative st little g. Oop. And because t is a dummy variable here, it's being integrated out, we can use any letter to represent t, like v or x or y or tau. We'll see. And just to check here, our integral up top is from tau equals 0 on up to t. So let's go through the proof. So first, we set up our transformation as the integral from tau equals 0 to infinity, to t, we'll get to infinity in a second, of okay, to start off our proof, we begin with the transformation of the convolution. Now these are both integrals. So we first have the transformation integral, t equals 0 to infinity of e to the negative st times the function we're integrating that happens to be f star g. So we introduce the integral from tau equals 0 on up to t of f of tau g of t minus tau d tau. That's the function we're integrating, and then we integrate with respect to t. So there is our nested integrals. What we want to do is to separate the two integrals out and to get them into the same limit form. To do so, we need to first form the double integral, and then from that double integral, see if we can pull it apart after first matching those limits. So, integral from t equals 0 to infinity. If we just stretch out the integration, throw the constant in, we have tau going from 0 up to t, e to the negative st, f of tau, g of t minus tau. It's all just thrown together. Okay, so there's our double integral. To separate it out, we first want to match the limits of our form on the right-hand side. And to do that, I'm going to draw the picture to see what's happening here. On the inside integral, I'm integrating in terms of tau, and that'll give me the inside initial low function, 0, and initial top function or upper function, t. And that means that we're cutting along the line tau equals t and going from 0 on up to t. So we have these vertical slices, and then t goes from 0 on all the way to infinity. So the region we're integrating over is this lower triangular piece of the first quadrant, but it's infinite in area. So we see that t is going to infinity. We want tau or some other variable to go to infinity as well. So we can rewrite the integration so that instead of slicing vertically, we could slice horizontally. And if we slice horizontally, the left limit is tau equals t, or t equals tau, and the right limit is infinity. And then the lower limit on tau is 0, and the upper limit is also infinity. So by rewriting the order of integration, we can get the right limits. Let's see. The function itself stays the same, negative st, f of tau, g of t minus tau. We're going to change it to dt, then d tau, which makes this inner integral go from the limit of t equals tau on the leftmost and t equals infinity on the rightmost. And then tau, we'll look at the extreme values. The lowest value is 0 and the highest value is infinity. Now we have that infinity in both integrals. The only difference between the form, well, there's quite a few differences, but the main difference in the limits is that we have one going from 0 to infinity and one going from tau to infinity. So I want to rewrite this limit as t minus tau equals 0. And that gives me the notion for what my new change of variables should be. So I look and I see another t minus tau. And so let's do a u substitution, in this case a v substitution, because u is a unit step function, we won't touch that, of t minus tau. And then dv would just be dt, because tau is treated as a constant in this inner integral. And if we go up to the top, we get infinity minus tau is still infinity. And that allows us to rewrite this t minus tau as a v equals 0. We can rewrite this t minus tau as a v. We can rewrite our dt as a dv. And then we have this e to the negative st. And here we can solve for t and get v plus tau for it. So we add e to the negative s and then multiplied by v plus tau. Okay, so now we have combined into a common double integral, and we have created the right limits by making a change of variables, a very slight change there. Now our job is to separate this out into a product of two integrals which look like transformations of f and transformations of g. So let's go back to the top. Separating out the f function, that means the tau piece. I'm going to pull out all the v components, so the dv, the g of v, and the e to the negative sv, and that leaves me with an e to the negative s tau. So I integrate from tau equals 0 to infinity, there's no v in those limits. And then another way to think about it, since I'm integrating in terms of v on the inside integral, I can factor out an f of tau, because that's treated as a constant, and I can factor out an e to the negative s tau, because that's also treated as a constant, and I'm left with the integral from v equals 0 to infinity of e to the negative s v g of v dv. And that equals the transformation of f times the transformation of g. And there we have it, proof that the transformation of the convolution is the product of the two transform functions. And because you can multiply the transforms in either order, it doesn't matter which function is f and which function is g. Pretty cool.